Question from May 2015, higher level paper 1 times on 1, and this question is from section B. So this reads, let un, where n is a positive integer, be an arithmetic sequence with first term equal to a and common difference of d, where d is not equal to 0. Let another sequence vn, where again n is a positive integer, be defined by vn is equal to 2 raised to the power un, and in a first part we need to show that vn plus 1 upon vn is a constant. Okay, so a part vn plus 1 will be equal to 2 raised to the power un plus 1, and vn is just 2 to the power of un. So we can rewrite this as 2 to the power of un plus 1 minus un. And from here we know that un is an arithmetic sequence, and basically we just subtracting two consecutive terms of this arithmetic sequence. So this simplifies to 2 raised to the power of d, where d is a common difference, and hence this is a constant because both 2 and d are constants. Now the second part, write down the first term of sequence vn. So v1, the first term, will be equal to 2 to the power of u1, and we know that u1 is equal to a right here, so we can write this as 2 raised to the power a. Now the third part, it says write down a formula for vn in terms of a, d and n. So hopefully we have realized by now that vn is a geometric sequence, because what we showed in part A is basically we divided two consecutive terms of this the sequence vn, and we showed that this is constant. So if the ratio of two consecutive terms is constant, that basically means it is a geometric sequence. So for third part we know that vn will be given by v1, the common ratio, to the power of n minus 1, and we know that v1 is equal to 2 to the power of a, the common ratio is 2 to the power of d, and this is raised to the n minus 1. This is answer to part 3. Now let's move on to the next part, b1. It says let Sn be the sum of the first n terms of the sequence vn, and we need to find Sn in terms of a, d and n. So since we know that vn is a geometric sequence, we can write that Sn is equal to the first term, which is v1, the common ratio to the power of n minus 1, divided by r minus 1. So this will be equal to, the first term we know is 2 to the power of a, 2 to the power of a, we know the common ratio is 2d, 2dn minus 1 upon the common ratio minus 1, which will be 2 to the power d minus 1. Okay, now the second part, find the values of d for which when I starts at 1 goes to infinity of vi exists. So basically this is talking about the infinite sum, and we need to find the values of d for which the infinite sum of this sequence exists. So hopefully we all know that the infinite sum exists when the absolute value of the common ratio is less than 1. This is the condition which is very important to solve this question. So we know that the common ratio is 2 raised to the power of d, 2 raised to the power of d, and this needs to be less than 1. Okay, all right, so let me make some space for this. Just give me a minute. Okay, so we can solve for d. So we can write this as either 2 to the power of d is less than 1, or 2 to the power of d is greater than -1. That's how we solve mod equations. So if I take log base 2 of both sides, I get d log base 2 of 2 is less than log base 2 1, log base 2 is just 1, so and this d is less than, and log of any log with base any base of 1 is just equal to 0, so this is 0. So we have found this first condition, and notice that this basically has no solutions because there's no real number of d for which we get -1. So basically, so this is our answer to this part. D has to be less than 0. And now, oh sorry, now the third part says you are now told that the infinite sum does exist and is denoted by s subscript infinity. We need to write down the infinite sum in terms of a and d. Okay, so the third part, the infinite sum of a sequence is given by the first term divided by 1 minus r. So we know that the first term is equal to 2 to the power of a divided by 1 minus 2 to the power of d, and this is the answer to this part. The fourth part says given that the infinite sum is equal to 2 to the power of a plus 1, find the value of d. Okay, so for this part, fourth part, we just need to equate this to 2 to the power of a plus 1, so 2a upon 1 minus 2d, this is equal to 2 to the power of a plus 1. Now from here we can solve for a, so 1 upon 1 minus 2 to the power of d, this will be equal to 2, this will just be equal to 2, because if we bring this down, this will be 2 to the power of a plus 1 upon 2 to the power of a. Then using the laws of exponents, this will be 2 to the power of a plus 1 minus a, so it will be left with 2. And then we can write this as 1 minus 1 upon 2 is equal to 2 raised to the power of d. I just skipped the steps, hopefully you understood this. And then we can write this as 2 raised to the power of d is equal to 1/2. So we can rewrite this as 2 to the power of d is equal to 2 to the power -1, and so we find that d is equal to -1. So this is the answer to the fourth and final part of this of B. Now the last part might be challenging, and it quite is. So it says let Wn, where n is a positive integer, be a geometric sequence with first term equal to p and common ratio q, where p and q are both greater than 0. Let another sequence Zn be defined by Zn is equal to natural log of Wn, and it tells us to find the sum of the first n terms of the sequence Zn in the form of ln k, with k in terms of n, p and q. Okay, so let's solve this question on a fresh page, part C. So what I can write as, first let me write Wn. So Wn will be equal to the first term p, the common ratio q to the power of n minus 1. I can write this like that, and so Zn will be equal to the natural log of p q to the power n minus 1. Now from here, hopefully we are familiar with the laws of logarithms, because they are quite important to solve this question. I can write this as ln p plus ln q to the power of n minus 1, and from here I can write this as ln p plus, I can bring the power down, so n minus 1 ln q. So now hopefully we can realize that Zn is just an arithmetic sequence with first term ln p, n, and the common difference ln q. In order to verify this, let me do this. So I'm going to do Zn plus 1 and subtract Zn from this. So basically what we're doing is we're subtracting two consecutive terms of the sequence of Zn. So, and if this subtraction gives us a constant number, that means this is an arithmetic sequence. So let's carry out this. Zn plus 1 will be equal to ln p plus n ln q minus ln p would be equal to ln p plus n minus 1 ln q inside the bracket. So simplify this. Oh, sorry. Now to simplify this. Oh, wait, my pen. Yeah, so okay. So this will be equal to ln p plus ln q raised to the power of n minus ln p minus ln q to the power n minus 1. So from here we can cancel ln p's and we are left with ln q to the power n minus ln q to the power n minus 1. And using laws of logarithms, this is ln q to the power n over q to the power n minus 1, and this will be equal to ln q. So now we have verified that this is an arithmetic sequence with common difference ln q. So now if we want to find the sum of this will be equal to n upon 2 times the first term plus n minus 1 times the common difference d. From here we'll just leave n upon 2 like that. So n upon 2, the first term is ln p, so 2 to the power ln p plus n minus 1. The common difference is ln q. Now further simplifying, we get n upon 2 ln to the power ln p to the power of 2 plus ln q to the power n minus 1. Now we can combine these. So this is n upon 2 ln p squared q to the power n minus 1. I need some space. Okay. So now what we can do is we can raise, this is just ln n upon 2 ln p square q to the power n minus 1. So we can bring n upon 2 as a power, ln p square q n minus 1 whole to the power n upon 2. This, now let's distribute the power. So this is ln p to the power 2 times n upon 2 q to the power n minus 1 upon 2, and this will be equal to ln, we can cancel the 2, p to the power n q to the power n minus 1 upon 2. So this right here is the answer to part C, and we have solved this question.